and krypton, and then you get these 3 other neutrons. Well, it turns out that the 3 neutrons that are produced, like the video we watched, A is for atom, those 3 neutrons can go and hit other atoms and continue the reaction. Remember, if you have a sample of uranium-235, there's going to be billions and billions and billions and billions of atoms in it. Now, if we can control that chain reaction, then we can use it to produce heat or to make a bomb or whatever we might want to do with it. So this is kind of the whole basis of nuclear power and nuclear weapons. So chain reactions is the important part here. The neutrons that are created will go and hit other uranium-235, and it'll make those break down, and that'll go and hit your other uranium-235, and that reaction can get out of control. But if we can control the speed at which it happens, then we can end up producing a bunch of energy or heat, and we can use that heat to do things. And there was a few scientists that were responsible for discovering this, and one of them was Fermi. And Fermi realized the materials could be absorbed, some neutrons could control the chain reaction. There was also this woman, and she is kind of one of these classic examples of how science in the 1900s kind of forgot women. So this is Liz Meitner, and she lived in Germany, I believe, and then during the war, World War II, she fled to Sweden, and she lived the rest of her life there. But she was the one who actually discovered how these atoms could be split and how this chain reaction could be continued. And she was actually studying this with a man named Otto Hahn. And Otto Hahn actually received the Nobel Prize for discovering this sort of chain reaction thing, and she didn't. And it wasn't till only a few years ago, like less than 5 years ago, element 109 on the periodic table was named after her in honor of her actually discovering this stuff. So because women often were forgotten in science, she didn't receive the Nobel Prize, but eventually she got an element named after her on the periodic table. So forevermore, she'll be element 109, which is meitnerium, which happens to be something that's really unstable and only created in laboratories, but still pretty cool. So there you go. So we're going to talk a little bit about CANDU reactors, and basically you just need to know that these things exist, and a little bit of how they work, and kind of some of the reasons why we use nuclear energy and why we wouldn't want to use nuclear energy. But CANDU reactors are really safe. They're recognized around the world for being really efficient, really safe reactors, and they can use fission decay of uranium that doesn't have really high amounts of uranium-235 in it. They have the ability to use really not very pure uranium. So we've sold them to Canada, obviously we have them, South Korea, China, India, Argentina, Romania, Pakistan. They all have CANDU reactors. So what happens is Pakistan says, hey, we need a nuclear reactor, and they contact the Canadian Nuclear Energy Commission, and they say, okay, we'll come over and build one for you. So we go over there, we build it, we train them how to use it, and then they use the reactor to produce energy for their needs, which is pretty cool. The kind of disadvantage to nuclear reactors is the waste that's produced. So we've seen uranium breaks down into krypton and barium, and that krypton and barium are highly radioactive. And the half-lives of these things are many thousands of years. So even after 20 half-lives, the bad stuff that's produced as a byproduct of these reactors, we don't know what to do with it. Now, recently in the United States, they've got a big mountain, they've hollowed out the inside of it, and they're just putting all of this nuclear waste in the inside of a mountain, because that's kind of how far we've gotten. Some of it gets purified and they pull out the good stuff, And there's still a bunch of stuff that's kicking around that we don't know what to do with. And it will be here and hazardous well beyond humans' lives. So the planet will be empty, I'm sure, one day, and there'll be a bunch of nuclear waste kicking around from when we use this stuff. So that's kind of one of the problems with this. Another problem with nuclear reactors is that they produce some really good stuff, like medical isotopes. So we can use some of the byproducts to diagnose things like cancer, thyroid cancers, medical imaging. We use all these radioactive byproducts. But another byproduct that's produced is plutonium. And if the wrong people get the plutonium, they can make nuclear bombs out of it, which is a bit of a problem. There's actually an interesting story about, I guess almost 10 years ago now, Iran, a country in the Middle East, was saying, oh yes, we're just pursuing a nuclear power in our country, and there's a few countries that didn't believe them, like the United States and Israel. And what happened is, when you want to purify uranium, you put it in a centrifuge. So you take uranium and you spin it really fast, and that separates the uranium-235 and the uranium-238 from one another. The uranium-235 is the good stuff for nuclear bombs, and the bad stuff is the uranium-238. It doesn't fission like uranium-235 does. So what actually happened was no one ever admitted to it, but everyone knows it was the United States and Israel together. They created a computer virus, and it was called the Stuxnet virus, and it infected computers all over the world. Like, just yours and my computers were infected by this virus, and it didn't do anything. And people were really confused as to why this virus was everywhere, not doing anything on all these computers. And it turns out that this virus infected the computers at the Iranian nuclear facility, where they had these centrifuges that were enriching uranium. And basically, once the virus entered the Iranian computers, it knew where it was, and it said, okay, this is kind of where I'm supposed to be now that I've infected millions and millions of computers. These are the computers we want to infect. And it basically turned on all of their centrifuges and just spun them uncontrollably until they just disintegrated. So basically, a computer virus that we think the Americans and the Israelis made infected the Iranian nuclear centrifuges and set their nuclear program back probably about 10 to 15 years, which is probably, I don't know, I'm not a political analyst, but it might be a good thing. So this is the inside of a CANDU reactor. Right here you have your reactor core, and this is a big containment dome made of concrete. So this is a couple feet of concrete. And in the reactor core, you have these little machines that put in new rods. So they put uranium in here. And in this red loop, we have water. It's generally heavy water, which is a special type of water. But the water circulates and it gets really hot, and it goes into a second loop, which also has water in it. And the steam gets created, spins a turbine, which spins a generator, which collects electricity, and then it gets condensed, and then it goes back in, and this second loop gets cycled. The third loop is always connected to some external water source. So you'll see that nuclear generating stations are always built on either a lake or a river. They need lots of fresh water to cool the core. Sometimes they can be built on oceans, but they have to desalinate the water generally. So the CANDU reactors are really safe because they have 3 closed loops. So the radiation that's all in the middle in the reactor core, it's contained in here. If something bad were to happen, it's all contained within this loop. So all of the radiation's contained in here. And then you have the second loop with just water in it, which is slightly radioactive, but not really. And then this third loop is just water from the outside, and it's not radioactive at all. So 3 different loops, very safe. No radiation leaves this reactor core center, and it's a great way to do things. There's other reactors that have 2 loops that are less safe, and all sorts of other stuff like that. So this is the idea behind this sort of chain reaction. You have a moderator, which is heavy water, which is kind of like H3O almost. instead of H2O. It slows down the neutrons. Neutrons can get going so fast that they don't get absorbed by uranium and they just zip right through them. That breaks down, 3 neutrons are produced, 3 more uranium split, 3 neutrons are produced here, 3 neutrons are produced here, 3 neutrons are produced here. It just keeps going. This is the chain reaction. Control rods are generally made of graphite, like the stuff in your pencil, and they actually absorb neutrons. So if you want to slow down a nuclear reaction, you put in the control rods down from the top, they absorb a bunch of neutrons that are flying around, the reaction slows down or stops. If you want to speed up reaction, you raise it up the control rods, the uranium breaks down faster, the more neutrons split, and that's how you can control a nuclear reactor. There have been 4 technically, but 3 major nuclear meltdowns in all of nuclear energy. So 3 Mile Island's in New York State, Chernobyl is in the Ukraine, and Fukushima is in Japan. So this behind me here, this big picture, this is Chernobyl in Ukraine, and the reactor melted down there. And they've created this large dome, and they're actually going to put it on tracks, and they're going to slide this dome right over the reactor because it's so radioactive there that nobody can really get close to the reactor. And if you can imagine, this is one of those cranes they build skyscrapers with. That's how big this dome is. These are cars down here, these little dots. You can see the little dots here. So that's a car. That's how big this dome is. So it's actually one of the biggest structures we've ever built. It's a couple $2 billion worth of construction. They're going to slide it over this to contain the radiation. They're going to start to dismantle the reactor that melted down. This is Fukushima. 3 of the reactors actually exploded during the tsunami. And what they're going to do here is, what's happening is all of the rain that falls on here is going down. It kind of goes through the reactors, and then it enters the ground. And the water from the ground is flowing out, and this is the ocean right here. So what they've decided to do is, they have a refrigerator plant, and they've drilled holes down into the ground all the way around the Fukushima reactor, or reactors, and they're going to freeze the ground and create an ice wall underground so that groundwater can't enter and then exit here. That's kind of how they plan on containing the radiation or the radioactive materials there from going right into the ocean. So kind of crazy, but that's how they're doing it. So that's fission. Does anybody have any questions on fission? Negative. All right. So fission, taking something big, generally uranium or plutonium, breaking it down into smaller things. A little bit of mass gets converted to energy, and you end up with energy being created. Nuclear fusion is something that takes 2 really small things like hydrogen or helium. It combines them together, a bunch of energy is produced, and the great thing about fusion is that the nuclear byproducts aren't radioactive. So this stuff here, if you can imagine getting a couple hydrogens, so these red guys are just protons. So you smash 2 hydrogens together, it creates this isotope of hydrogen. You get that and smash those together, and you end up eventually at the end of your reaction producing helium. So fusion takes hydrogen, which is the most abundant element, or abundant element in the universe, and it makes helium out of it. And you can fuse helium to make bigger things, but this is kind of the idea of how fusion works. So the really cool thing about fusion is that there's nothing bad produced. We get massive amounts of energy out of it, but no bad byproducts. We don't have radioactive materials with half-lives of thousands of years. So where does fusion happen? It happens in the core of the sun. The sun is one big fusion reaction. And we have started to harness fusion power, but we're not very good at it. Basically, the amount of temperature and pressure that needs to be created to fuse even the smallest elements like hydrogen and helium together it takes more energy to get these things to fuse than we're actually getting out of the reactions right now. We're getting close to being able to harness fusion power, but we're not kind of there yet. So that's That's kind of the goal, is to get cold fusion. And cold fusion is fusion that can happen at a temperature and a pressure that will allow us to get energy out. So at the bottom here, this is what a fusion reaction looks like. This is an isotope of hydrogen. This is deuterium and tritium. If we can get these two isotopes to stick, we produce helium, a neutron, and a bunch of energy. So that's kind of where we're at with fusion. We haven't harnessed it yet, but we're getting close. So let's do an example. We did a fission example for a warm-up. Now you guys can do this fusion one, and we'll see how you do. So if I can take deuterium and tritium, stick them together, I end up with helium, a neutron, and a bunch of energy. The 2 plus 3 is 5, 4 plus 1 is 5, 1 plus 1 is 2, equals 2 plus 0 is 2. Figure out what the missing element is here. Add up your masses on the reactant side, has to equal your masses on the product side. Add up your protons on the reactant side, has to equal your protons on the product side. What is the element? What is its mass? I'll give you a second. You guys should be able to get this one really quick. Math is very small and easy. You can probably do it in your head. What is there? What is that blank? Hydrogen, okay. Hydrogen's a good start, but is it hydrogen with 1 proton, 0 neutrons, or is it an isotope of hydrogen? I'm not looking for the actual name, but just the mass. Is it a kind of the standard hydrogen that just has a mass of 1, or is it hydrogen that has a mass of maybe something else? I'm going to take a little screen grab of it here, and we'll take it over. See if we can do it. Mass of 3, Abby says. Abby just showed up and she's throwing out answers already. I like it. All right, so we kind of separated at the arrow. It's kind of like an equal sign in a math equation. I have 6 plus 1, which is going to equal 7. Over here I have something plus 4, and it has to equal 7. So that's going to be a 3. So you can put a 3 there. And then on the bottom, I have 3 plus 0, which is 3. And over here I have something plus 2. So a 1 will give me 3. So this is a 1 and a 3. I look for element number 1 on the periodic table. I see that it's hydrogen. And this isn't hydrogen with a mass of 1 like it normally has. This is hydrogen with a mass of 3, which is an isotope of hydrogen, which is called tritium. You don't need to know that, but now you do. So yeah, there you go. That's a really easy example. And sometimes when you get to some of these fission examples, it's really good idea to go back and look at maybe some of the fusion ones with the numbers that are really small, easy to deal with, and you can kind of jog your memory and be like, oh yeah, that's how I came up with that. So yeah, you guys are right. You're on the right track there. And that's kind of it for fission and fusion. If you can do these equations, that's kind of the meat and potatoes of this unit. And those are the types of examples you'll see. You also end up answering questions about nuclear reactors, about why I've seen questions like why is nuclear reactors, why don't all countries have nuclear reactors? Why did Japan shut down all of their nuclear reactors after the Fukushima disaster? Why are countries moving away from nuclear power? Why are some countries moving towards nuclear power? So just being able to understand what's good about nuclear energy, like massive amounts of energy can be produced with very little reactants. It's carbon neutral, so when we break down uranium, we're not producing any carbon. And we have a really big problem now with energy burning fossil fuels and creating things like carbon dioxide. So there's absolutely no carbon involved when we produce energy with nuclear power plants. So what are some of the bad things about nuclear power plants? Why would we not want to generate power using nuclear power plants? Taylor, no, we don't end up ever talking about human anatomy in Science 10. I think you have to wait till Biology 12 even for human anatomy. Nuclear power. What's bad about it? Why? It's great in terms of the amount of energy that's produced, very little material in order to produce that much energy. What's bad about it? Why don't some countries like nuclear power? I can think of maybe 3 reasons off the top of my head. Any ideas? No ideas. Well, apparently I didn't do a very good job of talking about any of this stuff today. I failed as a teacher. Nuclear energy. It's hard to control. I wouldn't say, well, I guess we have very good engineers that can control this stuff. It's maybe a safety concern, right? You don't want this nuclear stuff getting into the wrong hands. If bad people in the world end up with some uranium, they could make a bomb out of it, or plutonium, which are byproducts. So the byproducts of nuclear reactors are bad. Either can be made into weapons, or they can be radioactive for thousands, if not millions of years. So the byproducts are really bad. Safety is a concern. When a hydroelectric dam, kind of one of the generators breaks down, it's no big deal. But when a nuclear power plant breaks down, really bad things can happen. You can get meltdowns. Thousands of people died as a result of the Chernobyl nuclear meltdown. So those are some of the reasons why nuclear power isn't kind of more widely used. There's a lot of safety issues with it. Money is important to talk about, but generally speaking, nations need energy. We need lights. We need things to power our houses and cars and everything else. So, a government will generally spend millions and millions of dollars developing some way to generate electricity, and then they'll charge people for it and slowly get the money back. So yeah, money is a concern, but it's actually a little bit cheaper than burning gas and stuff like that. We have about 10 minutes left. Yep, 10 minutes left. And this is not really part of the curriculum. I mean, it has to do with nuclear energy. But it's kind of like a history lesson. And there's a couple reasons I like to share some of this stuff, and kind of connects a lot of things that you guys are kind of aware of and not aware of. You're so far removed from World War II, but I think it's important to talk about. So I'm just going to kind of blather on here for about 10 minutes, and then we'll call it a day. I will get some more decay type questions for you guys for next day, and this is actually it for Unit 7. That's kind of all there is to it. So we'll actually jump into Unit 8 on Thursday's class, and I'll kind of wrap it up and answer any questions you guys might have in terms of Unit 7. So when's Unit 7 due? Let's make Unit 7 due on Monday. Unit 8 is up and ready to print. Yeah, Taylor, it's there. And I just want to talk about this real quick, and then I'll set you guys free for the day. So this was in 1939, and this is a letter. I'm not going to read the whole thing for you guys, but it's a really interesting letter. It's written from Albert Einstein. You guys are all familiar with Albert Einstein. And it was written to Roosevelt, who was the President of the United States. So at this point, it was kind of the World War II was happening. Einstein had fled Germany and moved to New York State, and he was just living there, being Einstein and smart and things. And he basically sent this letter to Roosevelt saying that, hey, there's some scientists. We talked about Fermi, Enrico Fermi and Leo Szilard were the two scientists that were working on sort of this theory that they could take uranium and they could break it down. And they had done studies, and because of people like Hans Otto and Liz Meitner had said, hey, this uranium is producing neutrons when it's breaking down, and these neutrons can hit other things and break those down, and it just creates this chain reaction. So Einstein said, hey, these two scientists have started studying this nuclear sort of decay, were really worried that it can be made into a weapon, and at this time, Germany had stopped exporting uranium out of Europe, and basically Einstein was saying they could probably make a bomb with this stuff. And he was telling Roosevelt to do something about it, else the Germans would come up with this weapon first, and it would change the face of war. So this is 1939. We hadn't started nuclear power plants. There was no bombs yet. Nothing crazy. People were fighting a war, but it was just kind of the environment at the time. And so basically, Germany had controlled parts of Czechoslovakia where there was uranium mines, and they stopped selling it into the public, not to the public, but to like other nations and things like that. So Einstein said, hey, uranium can do this crazy stuff, and the Germans have stopped selling uranium. So there's something going on here, and you guys need to deal with it. So what Theodore FDR, or Roosevelt, he started a program called the Manhattan Project. And the Manhattan Project was a secret project in order to create the first nuclear weapon. Now, there's some really interesting sort of connections. The A is for Atom talked about Oak Ridge, where the Manhattan Project took place. This is kind of where it was started out of. And basically, all of these dots all over the country, United States, they all worked independently of one another. Nobody really knew what was going on, but they were given a task, and the people in these big plants were doing these things, and they said, go do this, build this, and they didn't know why, and then all of these things were kind of happening all over the United States. You'll notice that there's 2 places in Canada, and one's actually really close to us, and Trail, BC. Has anybody been to Trail, BC? Is on the map here. Anyone ever been to Trail? Nobody's been to Trail before? You drive like east, and it's a small little community on the Columbia River. That's amazing. Nobody, there's like, anyways. Yeah, Shayna's been to Trail. What did you think of Trail, Shayna? The reason I talk about Trail is it was part of this whole Manhattan Project, but my family, not me, but my grandparents and my dad, they grew up and lived in Trail. And Trail's a tiny little town, and it has a big, it's called Teck-Cominco, and basically what they do is take rocks from all over Canada, and they refine the rocks down into ores, produce things like nickel and all sorts of stuff. You grew up in 100 Mile House. So Trail has a big smelter plant where metals were produced. Now, my grandfather actually worked for Teck-Cominco. It was called Teck at the time, or Cominco. Now it's Teck-Cominco. He worked there, and he was actually part of the Manhattan Project. He worked in secrecy in a part of the plant where no one really knew what was going on. And what they were actually doing in Trail was making something called heavy water, which is using an isotope of hydrogen. It's called deuterium, and they make water. And basically this heavy water is used in nuclear power plants as a moderator. It slows down the neutrons so the reaction can take place. So my grandfather actually got a certificate of recognition from the United States government for being part of the Manhattan Project. So that's why I think it's really cool. That's why I love this stuff. But what happened was in Trail, they made heavy water, and Trail is on the Columbia River, which kind of flows down into Richland or Hanford, Washington, where they had a nuclear reactor going there in Hanford. And in Hanford, they were refining uranium, which was actually mined in northern Canada. Up in the kind of Canadian Shield here was all the uranium that was used in the first nuclear weapons. In Richmond, they were making uranium-235. They were enriching it. In Oak Ridge, they're making plutonium. Down here in New Mexico is where the first nuclear bomb was ever detonated. And yeah, so basically this was happening all over the United States. All of these things were happening. So this is a picture of the Tekcominco plant in Trail. It's up on the hill next to the Columbia River. And all of the water that leaves Okanagan Lake flows into the Columbia River down through here. And this was the bridge that goes over the Columbia, separating the plant, and then Trails town is on the other side of the bridge. So that is Tekcominco, where heavy water was made, which developed the first nuclear weapons, which ended World War II. Pretty crazy stuff. I think it's always interesting to watch some footage of nuclear weapons being detonated because it's kind of scary and humbling at the same time. So I like to do that. Do you know how artificial reactions differ from natural radioactive decay? Interesting that there's a place in Africa where the concentration of uranium was so high that it naturally started to melt down right in the ground. So this happens in nature, Ava. There's actually a place in Africa where it's kind of the only natural known sort of chain reaction to happen outside of human control. Now, in a nuclear power plant, we can control the chain reaction. We make a reaction happen really slowly, and we can use the heat and stuff for that. If the reaction happens really fast, then we create a bomb. So there's really not a lot of difference between a nuclear bomb and a power plant, other than kind of the geometry of the reactor core is made in a way such that it won't turn into a bomb, but they melt down and bad things happen. So let's watch a couple of little videos here, and then we'll shut her down for the day. This is kind of a really dramatic music. So these people are witnessing nuclear bombs going off. So these are all fission bombs, and fission bombs create a bunch of energy really quickly. And you'll notice in all of the footage, some things happen. So you can see on like these transformers, the stuff looks like it's coming off of all these structures. And basically, what's happening is when a nuclear bomb goes off, it creates so much light and so much radiation that things like paint lights on fire. All these structures will ignite on fire because of the light that's created. So kind of think of it this way. If you're lying in your bedroom at night, your eyes are closed, and somebody sneaks into your bedroom and they turn on the lights. Even though your eyes are closed, you can still see a little bit of light through your eyelids. Now, if you were looking at a nuclear bomb when it detonated and you were close enough, a nuclear bomb produces so much light and so much radiation that even if your eyes were closed, you would go blind. That's how bright it is. So when you see nuclear bombs happen, or these detonations occur, all of the stuff kind of lights on fire because of so much energy is produced, and then the shock wave of the actual explosion hits and knocks things down. So it's kind of a two-step sort of destructive process. The first step is the radiation that's released lights everything on fire, and then the shock wave comes through and it puts out the fire and knocks everything down. And the actual amazing part of this is going back to Einstein's E = mc² equation. The actual amount of matter that's converted to energy in these explosions, the actual amount of matter that's converted directly to energy is less than a gram. So E = mc² is this kind of sort of really meaningful equation that doesn't really look that amazing at first, but the amount of energy that's produced, literally, if you took a penny and you cut it into 3 parts, if you could convert 2 of those parts of a penny into pure energy, that's what's going on when these bombs are exploding. That much mass is getting converted to energy, causing this much destruction. So that's why nuclear weapons are so amazing and dangerous. This is the largest bomb ever detonated. It's a 100 megaton bomb. It was detonated by, a 50 megaton bomb. It was detonated by the Soviets. And it's 50 megatons, which is 50 million tons of TNT. That's the equivalent. This isn't actually the bomb. That's one being detonated underwater. But here's the this 50 megaton bomb. the pilot that dropped the bomb barely survived. So you can see the mushroom cloud, and it doesn't really look that big or that scary, but that's kind of the crater that was created. But when we start talking about how big it was, there is the explosion from a long ways away. It's really nothing to really look at, but if we look at some of the facts associated with it, things like this. It was called the SAR bomb. SAR bomb was a fusion bomb, and the only way we can get atoms to fuse together is if we can get temperatures high enough and pressures high enough. And in order to make a hydrogen bomb or a fusion bomb go off, you start it with a fission bomb. That's the only way we can really effectively create temperature and pressure sufficient on Earth to make atoms fuse together, is by igniting a fission bomb first, which causes the hydrogen to fuse, which makes an even bigger explosion. So here we go. October 30th, 1961. It was originally designed to be a 100 megaton, but it actually detonated. They cut it in half to about 50 to 58 megatons. So that's million tons of TNT. That's what a megaton is. Here we go. It was blah, 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 it's equivalent to that many times. So the bombs that were dropped on Hiroshima and Nagasaki in Japan that ended the war, this bomb was 1,500 times bigger. Star bomb, I always forget all this stuff. The guy had, 45 kilometers away when he was in the bomb. Fireball and mushroom cloud, this is pretty incredible. The altitude of the Reese Plain was visible for almost 1,000 kilometers. The mushroom cloud extended 64 kilometers into the atmosphere. The atmosphere is only about 100 kilometers thick, so that's incredible. Over 7 times the height of Mount Everest. It went into the stratosphere, well into the mesosphere. Clouds don't go that high. It was 95 kilometers away. Basically, the heat from the explosion could cause third-degree burns. So a sunburn is a second-degree burn. A third-degree burn basically kills your skin. If you were 100 kilometers away, so 100 kilometers away from this bomb, if you were standing there, you'd get third-degree burns. So that means your skin would basically be destroyed, all 3 layers of skin. Shockwave absorbed in the air, and you could literally see the shockwave 700 kilometers away. And window panes were broken at distances of 1,000 kilometers away, even in parts of Norway and Finland. 1,000 kilometers. Think of something that's 1,000 kilometers away from Kelowna. So we're talking maybe in Saskatchewan. Is that 1,000 kilometers away, Mr. Ross? Yeah, about 1,000 K to Saskatchewan. So if this bomb went off in Winnipeg, or not that far, Saskatoon, you would be able to see the light. It would look like the sun was rising again if you were looking to the east. So that's how bright this thing was. In Saskatoon. Incredible. The energy actually measured an 8.1 on the Richter scale. The shockwave went around Earth 3 times, and it could still be measured on its 3rd trip around the world. So the shockwave went around Earth once, twice, and on the 3rd time it could still be measured on seismic recordings. It's just like, it's absolutely incredible to think that humans can produce something on this sort of scale and magnitude. It's scary, and yeah. How did I not know about this? You guys grew up in a time where you're lucky to be in sort of a non-nuclear sort of world where people don't take for granted these sorts of things, and they exist. I'm not going to watch this because it's about 10 minutes long and I've kept you guys a few minutes late already, but maybe we'll watch it at the beginning of next class. If you want to watch it online, it's really cool time-lapse map of every nuclear bomb ever detonated on Earth from 1945 when the first one was dropped in New Mexico, and then to 1998. And after 98, very few nuclear bombs have actually been detonated. Nations around the world have decided to not detonate them above ground because the radiation that gets released into the atmosphere is not good. And now the United States and many countries have computers that are strong enough to actually simulate what a nuclear explosion would do if they alter things. So basically, computers are powerful enough now to simulate nuclear explosions where we don't actually have to detonate these things. But we talked about North Korea, who doesn't have these big, super powerful computers, and they actually have recently detonated a few nuclear weapons just to test it out. Yes, Ava, for sure. So next class, we'll talk a little bit more about this. I'll find some more decay equations, half-life sort of stuff, and we'll spend some time reviewing for the test. There's also the module, I think it's module 2 exam, which is all the chemistry stuff together with this radiation stuff that's coming up as well. So we'll spend some time reviewing next day for sure. I think we don't need to get into chapter 8 next day, but if we run out of stuff to talk about, maybe we will. But let's plan on doing some review next class, and then we'll start chapter 8 the following week. And I'll have some more decay type equations for you guys, half-life stuff. I'll try to find some more nuclear equations because I know there's not a bunch in the learning guide. And then we'll talk a little bit about the module exam, and we'll leave it there. Hopefully that's all right. Thanks for staying a little bit late with me today, and we will start next day with some review. Does anybody have any questions before we go? Negative. All right, great. Have a great afternoon, guys, and we'll talk to you on Thursday.